As we've seen, multi-degree of freedom mechanical systems can be represented by ordinary differential equations written in matrix form. The solution of these equations is directly related to a well-known matrix problem known as the eigenvalue problem. Let's assume that we have a real symmetric matrix A. Consider the problem of solving AV equals lambda V, where V is an undetermined vector of coefficients and lambda is an undetermined scalar. In matrix theory, this problem is called the eigenvalue problem. The solution of the eigenvalue problem is a set of eigenvectors V and scalar eigenvalues lambda that satisfy this matrix expression. There are numerous computational methods for solving the eigenvalue problem, and many of them have been incorporated into software packages. Our focus will be on the interpretation of the eigenvalue problem and how the properties of the eigenvectors and eigenvalues can help us solve multi-degree of freedom vibration problems. Before we discuss the solution of the eigenvalue problem, let's examine the problem visually to get a better understanding of the meaning of the eigenvectors and the eigenvalues. Let's assume that we have a two-dimensional system, although the interpretation is valid for any dimension, and we choose an arbitrary vector v1 in the two-dimensional plane. Multiplying av1 will yield another vector in the plane. The eigenvalue problem states that the vector v1 and av1 must be equal to a scalar value. Another interpretation of this expression is that the vectors v1 and av1 must lie in the same direction in the plane. In the example on this chart, we have chosen a vector v1 that does not solve the eigenvalue problem. Likewise, in this example, if we choose a vector v2, we also note that v2 and av2 do not lie in the same direction. Therefore, v2 is not a solution of the eigenvalue problem either. Now let's choose a different set of vectors v1 and v2. For this choice of v1, we note that v1 and av1 lie in the same direction. Therefore, v1 is an eigenvector of the matrix A. Likewise, the vector v2 and av2 lie in the same direction. Therefore, v2 is the second eigenvector of A. Since it's a two-dimensional problem, v1 and v2 are the only two eigenvectors of the matrix. Now, once we've found v1 and v2, we can visualize the meaning of the eigenvalue lambda. Consider the case of v1. Lambda 1 is the scalar multiple of v1 that will make v1 and av1 equal in magnitude. For the example shown in this chart, lambda 1 is a scalar smaller than 1 since av1 has a smaller magnitude than v1. In the case of v2, the second eigenvalue lambda 2 will be a number greater than 1 since the magnitude v2 must be increased to make it equal to av2. Again, while this example was visualized in two dimensions, the interpretation of the eigenvalues and eigenvectors is the same for an n-dimensional system. Now, how do we solve for the eigenvectors and the eigenvalues of A? Rewriting the eigenvalue problem in a slightly different form by moving the right-hand side of the equation over to the left-hand side yields the first equation on this chart. Note that when we perform this operation, we need to multiply the scalar lambda by the identity matrix to maintain the appropriate dimensionality inside the brackets. This form of the eigenvalue problem states that the product of A minus lambda I and V must be equal to the zero vector. Let's perform a thought experiment. Assume for a moment that the matrix inverse of A minus lambda I exists. If A minus lambda I inverse exists, we can pre-multiply both sides of the expression by the matrix inverse, and the solution of the expression is the null vector v equals 0. Now this solution is not very interesting. Now let's assume that the matrix A minus lambda I is not invertible. Assuming A minus lambda I is a singular matrix is equivalent to stating that the determinant of the matrix is equal to 0. For an n by n matrix A minus lambda I, expanding out the determinant will yield an nth order polynomial in lambda as shown in the second expression. The eigenvalues of the matrix A are the roots of this polynomial expression. Now this polynomial expression is called the characteristic polynomial of the matrix, and the eigenvalues are often referred to as the roots of the characteristic polynomial. You may recall that solving for the roots of an nth order polynomial is a non-trivial task. Of course, in the case where n equals 2, the characteristic polynomial is a quadratic expression, and a general solution could be obtained from the quadratic equation. The case n equals 3 is much more difficult, but there are solution methods available. As we discussed earlier, the problem of solving for the solution of the characteristic equation has been studied extensively, and there are numerous computational approaches for solving for the roots of the characteristic equation and equivalently, the eigenvalues of the matrix A. Now, assuming we have obtained the eigenvalues of the matrix A, the eigenvectors are obtained through the solution of the expression shown in this chart. For each eigenvalue lambda sub I, there is an eigenvector v sub I that solves this matrix expression. This expression is solved for each of the n eigenvalues of A, yielding the n eigenvectors v sub I. Once a set of eigenvectors is obtained, the solution is complete. Now let's examine some important properties of the eigenvectors and eigenvalues of the matrix A. Writing the eigenvalue problem for the ith solution is shown in the top expression. We note that the equation is still valid if we multiply both sides of the expression by a non-zero coefficient alpha. This analysis shows that the eigenvectors of the matrix are not unique. As a matter of fact, there are an infinite number of solutions. What is unique is the relative size of the coefficients in the eigenvector v sub I. Another interpretation of this result is that we can scale the eigenvector by any non-zero coefficient and the resulting vector is still an eigenvector of the matrix A. Returning to the first expression in the previous chart, we can pre-multiply both sides of the equation by the transpose of the eigenvector v sub I. Note that once we do this, both sides of the equations are now scalars. You can confirm this by checking the dimensions of the eigenvectors and the matrix A. Now, since both sides of the expressions are scalars, we can now divide both sides of the equation by the dot product of v sub I transpose and v sub I. Once we do this, we see that we have an equation for the ith eigenvalue. It is the ratio v sub I transpose A v sub I divided by the magnitude square of the eigenvector. Recalling from the previous expression that we note that we can scale the eigenvectors to any magnitude. If we assume that the magnitude of the ith eigenvector is equal to 1, then there's a simple expression for lambda sub I. It is a scalar product of v sub I transpose A v sub I under the assumption that the magnitude of the eigenvector has been scaled to 1. The eigenvectors of the matrix also have properties that will be very helpful to solving multi-degree of freedom vibration problems. Once again, writing the eigenvalue problem for the ith solution, we can pre-multiply both sides by the transpose of the jth eigenvector, assuming that j does not equal I. Once again, we get a scalar on both sides of the expression. Now assume that we take the eigenvalue problem for the jth eigenvalue and pre-multiply by the transpose of the ith eigenvector. The symmetry of the matrix A allows us to write the second expression on this chart. If we compare this to the expression on the previous chart, we'll note that the term on the left-hand side of both equations is equal. Subtracting the two equations from one another results in an expression that is 0 on the left-hand side. On the right-hand side of the expression, we have the dot product of the two eigenvectors multiplied by the difference between the ith and jth eigenvalue. Now at this point we have to make an additional assumption. Assuming that the eigenvalues of the matrix A are distinct, we note that this equation is only valid if the dot product of the two eigenvectors is equal to 0. This analysis demonstrates that for a real symmetric matrix A with distinct eigenvalues, the eigenvectors of the matrix are orthogonal to one another. In 2 dimensions, this can be visualized by two vectors that are right angles to one another. Mathematically, this is expressed as the equation on the chart. The dot product of the ith and jth eigenvector is equal to a scalar multiplied by the operator delta sub ij. The operation delta sub ij is equal to 0 if I does not equal j and 1 if I equals j. This is a compact method of expressing the orthogonality of the two vectors. The scalar alpha is the magnitude of the eigenvector. As we discussed before, the non-uniqueness of the eigenvector means that we can scale the vectors such that alpha is equal to 1. Finally, the properties that we've proved can be used to decompose the matrix A into a diagonal form. Let's take the n eigenvectors and form an n by n matrix of eigenvectors V. Assume that the magnitude of each eigenvector has been normalized to unity. We we can write the product V transpose V and expand out each of the terms. When we do this, we see that the terms on the diagonal are the dot product of each eigenvector with itself, and the terms on the off diagonal are the dot products of each eigenvector with a different eigenvector. Since we assume that the eigenvectors are normalized to unity magnitude, and we know that the eigenvectors are orthogonal to one another, we can show that the matrix expression V transpose V is equal to the identity matrix. Another interpretation of this result is that the transpose of the eigenvector matrix is equal to its matrix inverse, under the assumption that each eigenvector has been normalized to unity magnitude. In the case where the eigenvectors are not normalized to unity magnitude, the matrix products will still be diagonal due to the orthogonality of the eigenvectors, but the on-diagonal terms would not necessarily be equal to 1. This property of the eigenvectors is also important to the diagonalization of the matrix A. Setting up the matrix product V transpose AV, we see that the on-diagonal terms are equal to the matrix product V sub I transpose A V sub I. The off-diagonal terms are equal to the product V sub J transpose A V sub I. Again, assuming that the eigenvectors are normalized to unity magnitude, we see that the off-diagonal terms of this matrix product are 0. The on-diagonal terms are simply equal to the eigenvalues of the matrix A. Thus, we see another important property of the eigenvector matrix. Once the eigenvectors of the matrix A have been found, the matrix of eigenvectors V can be used to diagonalize the matrix A through the matrix product V transpose AV. Similarly, we can show that the matrix A can be written as the matrix product V lambda V transpose, where lambda is a diagonal matrix of the eigenvalues of A. So let's summarize. For a real symmetric matrix A, we know that we can find a set of eigenvalues, lambda sub I, and eigenvectors, V sub I, that solve the eigenvalue problem. For the case of distinct eigenvalues, the eigenvectors were shown to be orthogonal and not unique. The non-uniqueness of the eigenvectors allows us to scale them to any magnitude. Under the assumption that the eigenvectors are each scaled to unity magnitude, we can show that the transpose of the eigenvector matrix V is also its identity matrix. This property was shown to enable the diagonalization of the matrix A through the matrix product V transpose AV.